Okay, am I on? All right, good. Hi folks, my name's Steve Watts. I'm going to be talking to you today about taking the guesswork out of your Hadoop infrastructure and operating systems. This is a joint presentation by Red Hat and our partner HP, based on work that we've both done over the last 2 years. Previously, before I was at Red Hat, I was the chief technologist for the Hadoop program at HP. So my agenda here is to clear up some common misconceptions. It's not really that difficult to do this. There's quite a lot of information, and the problem is that there's a lot of misinformation out there. So some of the issues are that, Hadoop sort of origined in around 2003, 2004 with, the Google white papers and the Apache Nutch project taking advantage of those. But basically, you've started around 2006 getting a lot of collateral hitting the web, and this is an example of collateral that's still out there on the web that's like wildly incorrect today. And so commodity architectures in 2006 and 2008 are wildly different to what they are today. And so, like as an example, with the web scale Hadoop origins, you had a single or dual socket on a server, so that's 1 or 2 processors on a server. They were 1+ gigahertz, around 1.8, 4 to 8 gig of RAM. So you still saw people running 32-bit mode instead of 64-bit. 2 to 4 cores, just a single NIC, and 2 to 4 1 terabyte SATA disks, right? So that means like 4 terabytes of total storage capacity per server. Part of the reason you see such pared down configs is, one, it was a lot longer ago, but also most of the collateral was being published by folks like Yahoo that have 4,000 node clusters, and where you seriously think extremely hard about cost per server when you have 4,000 servers, which is different when you're maybe an enterprise and you have 2 racks and maybe 40 servers, but both systems are in production, right? And so the reliability needs to be at parity between what you're seeing at web scale and what's running in the enterprise. But at web scale, you have different scale dynamics working for you, right? You can much easier tolerate a loss of a node at 4,000 nodes, much less disruptive than if you have 20 nodes, right? So the enterprise perspective is also different. And so commodity today is you're seeing dual socket, 2+ gigahertz, so typically I'd say 2.4 gigahertz is what I see most often. 4 to 48 gig of RAM, 4 to 6 cores, at least 2 to 4 1 gig NICs. As an example, HP for our standard rack mount servers will provide a NIC called flexible LAN on motherboard, right? The NIC basically comes in either 4 1 gig E or 2 10 gig E. So it's not like you're getting less than 4 just out of the box. And then your servers are typically between 4 to 14 disks with 2 terabyte and even 3 terabyte drives, right? So you're easily getting to 28 terabytes to 36 terabytes per node, right? So my point here is that you can quantify what's right for you, right? So effectively, you don't need to take someone's prescription of how to design a cluster. I'm going to give you some very simple models today that you can just apply and quickly put together and come up with your own approach that works for your specific workload, right? Everybody's workloads are different, and that's why it's so hard to prescribe an approach here. So the trick is balancing the performance of the cluster with storage capacity. At some points, these things can be at odds with each other. And in addition, you want to get that at a premium price point, right? There's lots of ancillary costs that folks that maybe come out of software engineering don't necessarily understand, like in the data center. Did you know that the power and cooling costs of a data center are 1/3 of the acquisition of the equipment itself? So 1/3 per year, right? So if you bought a rack for $300,000 or euros, it costs you 100,000 euros a year to power and cool that, right? So you really want to think really hard when you start getting to large-scale dynamics, right? Okay. So the first thing you do is you instrument your cluster. Now, sadly enough, nobody ever seems to do this, right? And there's a lot of paper exercises about how to optimize Hadoop, but nobody ever does this. In fact, Alan, who presented yesterday, is one of the few people that I've met that actually does this, and he chirps me on Twitter every time I throw this slide up, so I've now put in a little excerpt for him. So the approach is really simple. You instrument your cluster, you run your workload, and then you analyze the numbers. So what you see in this picture here is Andy Lerner, from the HP performance team. He actually now works at MapR. We've got, every time we publish a white paper or reference architecture white paper at HP, we actually buy the equipment and then build it and optimize it and tune it. So everything that's being described in the white paper is actually being built and run in the labs. So you're seeing a MapR cluster on the right and a Cloudera cluster on the left there. And so what you're seeing, if you notice, there's quite a lot of cables on the right? And so with the MapR, we're doing 4 bonded 1 gig E, and with the Cloudera, playing around with 2 bonded 1 gig E, right? So there's half the cables around. But we basically tune the options and then, grok the numbers and make our decisions based that way. So the key thing here is don't do paper exercises. Every single time that we've come into, a design and say, theoretically, this workload should behave this way, Hadoop has proven us wrong. There's so many different variables in the system. The only way to really properly understand this is to run this. So here's an example. You'll commonly hear from folks that are pseudo-knowledgeable about hardware infrastructure design that they'll say something like, TerraSort is IOBound. It's an IOBound workload. Graph processing is a network-bound workload. Machine learning is a CPU-bound workload, where that's not actually true. It's equal parts application and equal parts infrastructure that define where you're limited in your performance capabilities for your application. So I'm actually going to walk you through a particular workload and show you that with this particular server configuration, TerraSort's not IO-bound in any shape or form whatsoever. So what I'm going to do is the approach that we take is we typically over-provision a little bit, and then we look at the stats and then figure out how to tune the configuration down by cost to keep the same performance, right? And so what we're doing here is we've got identical server designs, with the exception of the Hadoop slaves have a lot more storage capacity. Okay, so we have a 42U rack. So for those of you that aren't familiar with rack design, 42, each U is about an inch, and there's 42 U's in a rack, and servers typically come in a 1U width, or a 2U width, or a 4U width, right? And so basically we have a 1U server for the job tracker and a separate 1U server for the name node. They don't need the extra space for all the additional disks because they don't have significant storage requirements. And then we have 18 2U servers that are actually our Hadoop slaves running the data node and task tracker processes. And so the actual design of these servers, they all have 64 gig of RAM, so they've got lots and lots of memory. Another misconception I hear is, I have a high memory workload, I need to scale out because of this. You should be aware that, your standard rack mount servers can, if you get special kinds of memory, can go up to almost 900 gig of RAM, right? But we've got a lot for Hadoop, 64 gig of RAM. We've got 2 sockets, 6-core Intel 2.9 gigahertz processors. So we've got a lot of cores. 6 cores, really what I define as the commodity. It used to be 4. It's really the price has come down for 6 cores. So I would say 6 cores is your commodity, and 2.9 gigahertz, that's the fastest 6-core processor Intel has, right? So it's a very fast processor, and you could certainly get cheaper processors, right? And I'll talk about that later. And then, so that's sort of the memory and the processor. Now let's talk about the I/O subsystem here. We've got 2 controllers, right? And we have 16 disks, and this is very specific, right? With each drive cage, it has 2 cable attachments to each drive cage for the SAS lanes that come out of the controller, okay? And you can put 4 SAS lanes for each cable. So basically there's 8 SAS lanes per drive cage. So each lane goes to 1 disk, okay? So 8 lanes, 8 disks, which means that every disk has its own dedicated SAS lane for communication through to the controller. This basically means you're not going to get any throughput issues that will lead to bandwidth issues, okay, for accessing your disks. So we can actually support 2 of these drive cages in this particular setup. So we have 16 disks, which means every disk has its own lane, so we can fully drive 16 disks. Now, why do we have 16 disks? Because the more disks that you have, the more you can spread the I/O requests across the disk. What you don't want is if I map this over to Hadoop, many different Hadoop slots configured, each with their own thread, hitting the same disk at the same time, accessing different blocks on that same disk, right? So you want to basically increase the likelihood that the block will be on another disk, and that basically it can get its own lane directed to it. Okay, so then lastly, I have 4 bonded 1 gig E NICs. So that's basically 4 gigabits a second of read throughput and write throughput, so that we shouldn't basically be network bound. So that's the high level, hypothesis. So what we do, we ran a 10 terabyte terasort. So one of my favorite rants is, you see people publishing 100 gigabyte terasort benchmarks. One terasort isn't particularly useful as a benchmark in that it's not very representative of a lot of Hadoop workloads. It's actually useful in that it's a well-understood benchmark as far as what it does, which is part of what you want with the benchmark, but the other part is being representative. But it's an example workload, right? Really what you want to do is replace terasort with your own workload, whether it's a k-means clustering algorithm or something to that effect. Okay, so you instrument the cluster. The main point on this slide is that you use whatever framework you're comfortable with, right? It might be Ganglia. For us, at HP, we were using we'd been doing database benchmarking for years and years and years, and for that, we've always used the Linux SAR tool, right? And so the way we captured the metrics is we had an outer script that shelled into every node in the cluster and started the Linux SAR capturing process, right, for capturing all the metrics going on that node. And then once all that had happened, the shell script then started the Hadoop job and submitted it. So this was not obviously TeraGen, this was the following one, TeraSort. And then after the Hadoop job submitted, it waits until the job completes, and then it shells into each node and stops the processes. So at that point, then what we do here is that we pipe the information out, so you can actually pass in commands to the actual DAT files produced by the SAR tool. And you can extract specific metrics around CPU utilization, I/O information, network devices, and we pipe that into CSV, and then we loaded it into a MySQL table so that we could do ad hoc analysis on this if we really needed to do some deep diving, which is easier to do that way with SQL than it is with Ganglia. Okay, so what did we find out? So keep in mind, the first thing you want to do when you're trying to sort of grok the performance of your I/O subsystem is run a Linux tool called the DD test. And the DD test will figure out your total I/O read and write throughput of your disk subsystem. So effectively what you should be seeing, given current state of the art, is 100 megabytes a second of throughput performance, right? So typically if you have 16 disks, you want to see 1.6 gigabytes a second of throughput performance. So let me explain the chart. On the x-axis, you have megabytes a second. Sorry, x-axis is time, so it's duration of the job. You can see a sort of abnormal spike there is the reduce shuffle and then the reduce phase, and the sort of fairly consistent before that was the map phase. And on the x-axis is the megabytes per second that's being used for throughput. Now, if our total is 1,600 megabytes a second, you're seeing that with this disk subsystem, I'm at 10% of my total capacity, utilization capacity. So I'm not IOBound in any shape or form, okay? So this is goodness. Effectively, if you're seeing numbers like this and you're hitting your performance objective, the next order that you put in for your hardware, you should greatly reduce, you can save a lot of money. I mean, your hardware, your I/O subsystem infrastructure for your I/O subsystem components for your server are way over provisioned in this example. Okay, so let's look at the next thing, which is the network throughput, right? So we've got 4 bonded 1 gig E NICs, which is roughly 4 gigabits a second or 400 megabytes a second. And if you look on the x-axis again, it's elapsed time. And on the y-axis, it's throughput. Again, just like the other one, right? So if we have 400 megabytes a second of total throughput, we're averaging somewhere between 60, 80, which is like roughly a quarter of the total capacity. So we're not network bound whatsoever. So now to you, your next takeaway should be, well, a lot of people are trying to sell me InfiniBand for my Hadoop cluster, right? That's nonsense. If this is your workload and it's performing like that, there's no reason to buy InfiniBand, right? So I'm not network bound whatsoever. Now, let me give you an example. When we ran this test with like test DFS IO, which does lots of reads and then lots of writes, it lit up this NIC, and we're starting to max out the network performance. We still had some, but I think we're at like 85% capacity. So if that's like, say you're doing a graph processing algorithm, and graph processing algorithms are notoriously difficult because it's hard to collocate all the edges in the graph on one server. So by nature, you're seeking across the network to find aspects of the graph that you don't have on your own machine. And so that might well be the case. And then you might want to go to 10 gig E. But I'd scale normally that way. So now here's the key thing, right? The main premise with your design here is that you want to keep your CPU as busy as possible, doing as much work, the server doing as much work for you as possible, because that'll boost your performance up. What you've got to do is make sure that you can remove any impedance to keeping the CPU busy, which is I/O wait time, right? So how much is the CPU waiting on instructions, and it's getting sort of impeded by either the disk subsystem or the next network subsystem. So here we're seeing our CPU getting slammed, which is great. But the I/O wait time is negligible, which is perfect, right? So I have my I/O subsystem and disk subsystem configured the way I'd want for great performance. It might not be for great cost, though, right? So I might want to start eating a little bit less performance by tuning down my I/O network subsystems to save a lot of cost. I think in Alan's talk, you saw a lot of examples where he basically made different trade-offs. So here on the memory slide, this is anecdotally interesting, but contributes to why there's no I/O wait time. So you see the memory consumption is fairly full, which is the blue. The red is the percentage of data that is cached in memory. So this is how much data is cached in memory, so that any time there's an access for data, the CPU can get it directly from the memory and is not going through the controller and the I/O subsystem to read it off disk, which greatly aids performance, right? So we're efficiently using memory. So this is the last metric that you should look at. Potentially, if you're getting a high I/O wait time and you're seeing good performance, you're not seeing any impedance in the disk or network, then you might want to look at this chart and see if you have some issues going on with memory. So at that point, basically, you can sort of see how your workload fared and how it's matching up with the infrastructure. Now, this is sort of my general guideline chart, and I'm going to walk you through the different trade-offs that you can now make, right? So say you've over-provisioned your infrastructure and you want to go for a slightly lower cost for one particular workload. Let's start at the data center. Always talk to your data center folks. There are realities around space in data center. You might, there's also realities around how much power you can that is available to be provisioned in the data center. So effectively, data centers are carved up into floor tiles, and a rack goes on a particular floor tile. They're about that big. And there's only so many floor tiles available. Now, there's other realities around the data center in that basically they only have so much power that they can provide per floor tile, right? And so even if they can provide power to every available floor tile where you could put a rack, they might not actually be able to power the total needs that you have in your rack. So your power footprint might be really, really high for your rack, and you can't actually push that much power to the particular rack, right? The other thing is that when you have all these different components running, you get a thermal footprint. Your rack is generating heat, and you've got to actually be able to cool this down. And so there's depending on the cooling infrastructure, there's only so much that you can cool per rack. So you've got to figure this out before you do anything else, right? Okay, so then the next aspect is the I/O subsystem. I spoke about the controllers, right? Imagine if I changed that architecture and gone from 2 controllers down to 1. Then I would be sharing lanes with disks, and then I would basically have some degraded throughput, right? This isn't a train smash. I'm actually going to go and one of my following slides recommend a generic Hadoop server design that works for pretty much all workloads that is configured that way. So that's the one aspect. The next is the amount of disks. I mentioned that you want as many disks as possible to get the best IOPS, right? To be able to spread the IO out around the disks. However, disks come in different sizes, and there's limitations. Like if you're buying a 1U server, you can put probably 6 to 8 small form factor disks, which is a 2.5-inch disk, right? But they cap at about 1 terabyte. And that disk is exactly the same cost as a 2 or 3 terabyte, 3.5-inch disk. okay? So ideally, you want a lot of storage capacity for HDFS. So you don't want small form factor disks, you want large form factor disks, but you want a lot of them, okay? So, so I mentioned storage capacity. Then there's the aspect of RAID versus JBOD, right? So you'll hear lots of people tell you, don't do RAID on your Hadoop clusters. This is a factor that can change with scale. If you're running a cluster in production with just 1 or 2 racks, and there's an impact to the business for every hour your Hadoop cluster is down. We had a customer at HP that this was the case. What you want to make sure is that cluster is as available as possible. Now, if you lose a whole node and you only have 20 nodes, it's kind of a big deal. You've got block replication affecting your network traffic, and you've lost one particular machine doing work. It's a very easy, inexpensive solution to at least do one RAID mirror on the system, where you put the Hadoop OS and runtime on one really inexpensive 500 megabyte disk, and mirror that disk, and then you keep the other 12 drives in the 2U server in a JBOD-like setup for the data drives. And the way you do that is you have your single RAID controller set up a mirrored volume there, and then for each of the other 12 drives, you have individual RAID 0 drives. So now there's, when I say this, people have this aneurysm. What? I've read in Tom White's book, JBOD is faster than RAID 0. Yes, that's true, but what they're talking about is taking all 12 disks and putting them in a single RAID 0 volume. If you put each disk in its own RAID 0 volume, you effectively are producing a JBOD, right? So they're talking about a different thing. Okay, so that's the disk subsystem. On the compute, this is where you need to start factoring in power, right? So Intel has 2 sort of series of processors. They have the socket R, which is the high power, high performance processor, and they have the socket B, which is a lower power, slightly lower performance processor. Now, going back to that point I made about power and cooling costs being 1/3 of the cost per year of the total acquisition of the equipment, I would advocate going with lower power, 95-watt socket B processors versus 130-watt socket R processors. And you're basically looking at the differences, a 2.4 gigahertz 6-core processor versus a 2.9 gigahertz 6-core processor. So I spoke about the amount of cores already. The choice of the processor affects the amount of memory that you can provision. A socket B processor has 3 memory channels per chip. A socket R has 4 memory channels per chip. So if you're putting 8 gigabyte DIMMs, that's the difference across both processors, right? Because each processor has its own set of channels. It's the difference between like a 48 or a 64 gigabyte server, if you're using 8 gigabyte DIMMs. So that's something to think about depending on your memory needs. If you're maybe using a NoSQL solution like HBase that needs a bit more memory than MapReduce, right? So it can keep as much data as possible in memory without seeking to disk. Lastly, on the network, you're looking at 1 gigi versus 10 gigi. One of the questions, so there's a couple things to think about here. There's also redundancy. If you have just one NIC on your server, okay, then if you lose that NIC, that whole server goes offline. And Hadoop's default behavior is that anytime a server goes offline, the name node realizes it, and basically the blocks that are on that server will get recreated elsewhere. So there'll be an auto-replication operation that will occur. So there'll be an impact to the network. So what you want is to basically at least do 2 1 gigi NICs, unless your scale is so large that, or sufficiently large that you can tolerate a loss of a node and the incidental replication that occurs without really affecting your performance, right? Basically letting Hadoop do what it does. Okay, so the next thing is, but if you're doing 4 1 gigi NICs, which can be quite standard with Dell and HP's 2U servers, you've got to make sure that you have available port count on your switch. So you need switch with at least 96 ports, and you need 2 of them. Because if you lose a switch and you only have 1, you lose that whole rack, and then basically you're just going to crash your cluster with a block replication, right? If you only have 2 racks, right? You're going to have a lot of replication. So last thing, I haven't actually done any analysis. This is one of those dangerous hypotheses, but Hadoop is a has a phase in it which is bursty for network traffic, which is the shuffle and sort, right? Where basically, all the maps run and the network goes quiet until the maps largely, roughly the same time, basically produce their map output and it gets shuffled and sorted, which then has a lot of network traffic going on. So the theory is deep buffering, switches with deep packet buffers, so they can take a lot of packets that back up while it's still routing the other ones, is goodness, because then packets won't get dropped when it gets slammed with network traffic all the time. Okay. So this is good, but I've taken you through a process of just basically tuning a server for one particular workload, which I think was good, and I wanted to share that with you. But in reality, you don't want to get into an issue where you have Hadoop clusters popping up all over the place. It can become an admin and ops nightmare. I think what you really want to do is get to a very small finite number of shared Hadoop clusters, which have many customers within your organization. So you're running multiple workloads on them. Especially if you're using various different schedulers, you can have multiple concurrent workloads from different customers all running at the same time. So you want to avoid this Hadoop whack-a-mole situation if you're in ops. So what you really want is a server design that's balanced and can support a wide variety of different workloads. And so my proposal is this, right? For the name node and job tracker, it's the identical one that I spoke about there, right? It's a 1U server, single controller, 64 gig of RAM. It's got very performant processors in there, potentially over-provisioned, but I'll explain why. And then basically doesn't have a disk requirement, doesn't really need to store much memory, so you basically have 4 small form factor disks done in a RAID 1+0 or RAID 10 configuration. The Hadoop slave is different than what I started with, right? This is 2U, 48 gig of RAM. Okay, so this is the socket B. This is the lower power processor, right? So you're going to have, your whole cluster is going to be full of this server, right, the one on the bottom. And so you want the lower power processor to save on operational expenses. And just a single controller with 12 2 terabyte large form factor disks. So that basically gives you a sufficient amount of disks for performance, but they're 2 terabyte large form factor disks so that you get quite a bit of storage capacity with that. So 24 terabytes per node. And these servers typically are actually 14 disk servers. There are 12 in the front, and there's 2 at the back. And the 2 at the back support the ability to do the RAID 1 mirroring should you choose to do so. If you don't, you can use them as data disk too. Okay, so we have, so that's basically your server building block. Now let's talk about rack design. So the reason I somewhat over-provisioned the job tracker and the name node is I want to prescribe an approach where you can create an initial building block for your master rack, right? The rack that runs your name node and your job tracker, and you can scale that out to Hadoop's scalability limit without ever having to come back and change the hardware in this initial rack, right? So essentially the way this is designed is, so this is the initial building block. You have 2 switches, so 2 1 gigabit top of rack switches. If 10 gigabit is something you can afford, more power to you, do that. I think the price is coming down, and it's almost at the point where people are just buying 10 gig anyway. 3 management nodes, so basically one of those is the job tracker, one of those is the name node. You want to create a private network for your Hadoop cluster to basically keep other application traffic segmented away from your Hadoop cluster. That's one reason. The other is to keep the users out of the actual ability to tamper with the operational capabilities of the server, so to actually keep them off the name node and the job tracker. And so to do that, then you actually still need to have users the ability to provide jobs. So you've got to have a management server or a gateway server or an edge server. It's called many different things, but it's multi-homed onto both the private network of the Hadoop cluster as well as the user network. So users can shell into that, submit pig and hive jobs, or copy in a MapReduce jar to be submitted, or they can load up some sort of management console like Ambari, where they can sort of see the progress of their jobs. And then you have the rest of the server is filled with the Hadoop slave, right, that runs the data node and the task tracker, right? And so that's the exact same design. So assuming that you have this, then to scale this design out, so the single rack is the one we just described on the initial building block. The extension is the stuff that you see that has detail inside of it. And so basically you have one or more of these extension racks, and they're very similar. They basically have 2 switches in there. You may drop that down to 1 if your cluster is sufficiently large, but, and then it's basically filled with Hadoop slaves. Now the trick here is that you want to be able to integrate these 2 networks, and while they're running 1 gig, you should at least have a 10 gig core aggregation switch, which you're wiring the 2 top of rack switches into to extend the network. And so basically using this sort of building block approach, you can just keep adding these extension racks. Okay. So on Linux optimizations, the first thing we noticed, turn off caching on the controller. We found on the HP controllers that if we turned the caching off, we'd actually get a performance increase. The next is what we've seen most people use, and actually in discussions with different vendors, like, well, if I put myself back as an HP employee, what we were getting from Red Hat, what we were getting from Hortonworks, from Cloudera, was basically rel 6.1, and then basically mount your volumes with the no access time setting. So basically what this is with Linux, every time you access a file, it tracks when the last file access was. And so there's a slight write to the file system. It's a tiny one, but it's a write to the file system that tracks the last access time. If you remove this setting, then you get an improvement in read performance. The other thing is this transparent huge page compaction creates quite a bit of overhead for Hadoop jobs, so recommend disabling that if you're using rel 6.2 or later. That's the most significant, I guess, setting I've found for 6.2 as far as causing impact. Optionally, if you want to do name node HA, Red Hat has an HA kit for this. So this is essentially basically you take one, instead of having a single name node, you have 3, and then you basically have you have all 3 connected to a single NFS mount with shared storage, and then you use power fencing, and it just the HA kit provides the high availability and the switching between the 2 in the event of a disruption. Lastly, I did want to say that I'm in the process of doing EXT versus XFS analysis. Initial findings are that XFS can provide a significant performance boost, but I don't really have any numbers there. I just wanted to let you know that I'm looking at it. Okay, and this is the last slide, which I find interesting, right? So right now, what's great about MapReduce is that you have very fine-grained control as to how much work a particular node is able to do by configuring the slot allocation. So you can say this node has 2 map slots and 1 reduce slot, or it has 20 map slots and 5 reduce slots. It's arbitrarily configurable. So we're starting to see in the industry that there's an over-provisioning of your standard commodity server that I showed you in the first slide is sort of over-provisioned for the bulk of workloads, right? So now there's 2 ways to approach that. One is you can say, oh, well, commodity servers are over-provisioned. Let's enter the world of virtualization, and we can carve the server up, and we can allocate it equitably amongst the different applications and give them just the right amount of resource they need. The other way, so that's the software approach. The other hardware approach is to get to sort of these microservers, where you're basically looking at a 4 to 8 gig of RAM, 4 cores, 1.8 gigahertz, 2 to 4 terabyte, 1 gig Enix. Now, what's kind of interesting is I have this as in a continuum because Hadoop sort of come full circle. These are effectively the same stats that I showed you from 2006. But here's what's different. So when you go to a rack, and if you sort of, a typical JBOD is in a storage drawer. So you go to the rack and you pull out this drawer, and there's all these little disks. It looks somewhat like this, right? And there are those 3.5-inch, 2 terabyte disks that I spoke of. And you sort of pop them out and eject them. So we've now, well, at HP, we basically got this Moonshot program where we were taking Intel Atom and ARM processors and producing server cartridges that are effectively the same size. So what you see here is a tray, and each one of these cartridges, which is about so big, is an actual server, right, with these specs. And running Hadoop quite well on these. They haven't quite hit the ability to get 64-bit yet for the ARM, but it's coming. But it's kind of an interesting approach, and especially around density. So typically on a normal rack, you can put in about 20 servers, right? With this approach, you can get 270 servers per rack with an increase, it's about 100 terabytes more per rack of storage using this architecture than a standard 2UX86 architecture. So it's somewhat interesting, but again, it's sort of low memory. So that's one of the issues. So Trevor Robinson from Zeta I live in Austin, Texas, and he lives there too, and that's where Zeta is based. And he's working in the Hadoop project, but it's somewhat frustrating for him because we have such a surplus of memory on the standard Hadoop server that nobody's overly worried about memory management or super granular memory management, which is what he has to do. So anyways, if you're so inclined, there's his address, and he's keen to work with you if you're interested in that. So I have about 4 minutes left for questions. I just want to thank our partner HP for letting me present our findings. And if you're interested in learning more, everything that I've articulated in this presentation is in these HP reference architectures. They're about 30-page PDFs with only the last 10 or so pages around actual recommendations. The first 20 pages is preamble explaining how we got to those recommendations. So those are available on the Hadoop website. So thank you very much. That's the end of my talk. Are there any questions? Sure. Yeah, so truth in disclosure, I haven't tested AMD, so I don't have data for it. I think what I would recommend is, probably one thing I should have touched on a little more is tuning your slots, right? So actually in Alan's talk, he spoke about he got a performance boost by cutting the amount of slots that were allocated. So what you've got to do is basically, regardless of what processor you're using, whether it's Intel or AMD, I'd look at the power consumption. I wouldn't focus too much on the cores. I'd focus on the price. It's probably 6 cores. I know AMD has like the Magna Core stuff with more cores, but what you want to look at is how many slots you're running and how much work you're able to actually get out of that, and basically sort of run through the same exercise. But I know I have friends running relatively large clusters, in fact, with AMD processors, and also some of the most detailed analysis I'd ever seen on Hadoop benchmarking was from AMD about 3 years ago at the Hadoop Summit in Santa Clara. There was a little guy hiding in the back of the room with this poster session, and it was like ridiculous, the amount of like arcane information that's almost impossible to get that was on this thing, So I know for a fact that they're doing a lot of work on it, so I just haven't tested it, but I think they're legit. Steve, I'm going to regret this, aren't I? Well, our performance team, Red Hat performance team, is already doing that. So there was quite a bit of work. So if you saw, Red Hat has made an announcement that we're enabling Hadoop to run on GlusterFS. And there was quite a bit of work last year, prior to me joining Red Hat, where our performance team in Massachusetts had actually done quite a lot of benchmarking on that. So it is my understanding, I can't make a formal commitment on part of the company, but it would have to be part and parcel of our plan to support Hadoop on top of GlusterFS. Yes? Yes. It is. You can't do straight pass-through like an HPA adapter with a RAID controller. So that's basically the only way to get a JBOD-like configuration with a RAID controller. Absolutely. No, all our testing at HP was done on EXE3. But as I said, I'm looking at it. The XFS is stable for me, but I haven't done an A/B comparison between, it's somewhat interesting in that, like, with Hadoop, you sort of look at what the big players are doing, like Yahoo, and running at scale. And since you're not running at that scale, but eventually you'll get to that scale, people just sort of take their recommendations ad hoc. So I think the standard Yahoo, full scale, as well as what we're hearing from, I think, Cloudera and Hortonworks, ext3 is basically what you want to go with for now. But I want to validate that. I want to actually see some data as opposed to somebody saying, Alan, yes. Is it ext4? Okay, yeah. The guy behind you, I'll get to you next. So there's a couple of issues. So there's nothing wrong with virtualizing. In fact, it can be quite an efficient ops technique where you maintain a particular image that gets deployed out on all the machines, and then it's easier just to maintain that one image as opposed to 50 separate machines. The problem is when you start virtualizing storage. With Hadoop, you always want to make sure that you can preserve the data locality. Right, so you want to make sure that you can virtualize the compute, but don't virtualize the storage. So if you want to just virtualize the compute, I think there's a slight 1% hit that you might take on performance or something like that, but I don't have any issues with that. You, sir. Would you mind saying that again? I/O schedulers? I'm sorry, I don't know. I'm sorry, yeah, which one? Yeah, I don't know off the top of my head. I'm sorry. Yes. Can you say that again?
So disabling the journaling on XT3 seems like just override things like Hadoop certificating everything. Is not a gain or is something that might be an option?
I don't know. I haven't run that test. I'm sorry. Any other questions? Well, thanks, everybody.